thanks everyone for joining this session, yet another session by PAS. And today we have with us Dr. Prajval Shastri. Uh, Thank you, Dr. Prajval Shastri, for joining us. So, Dr. Prajval Shastri has been an astrophysicist for over 35 years, and her core research interest is in the empirical investigation of giant black holes that are found in the centers of distant galaxies. So, so she basically studies the phenomenon of accreting supermassive black holes, and she used the data from telescopes that operate at radio, infrared, optical, ultraviolet, X-ray, and gamma ray frequencies for her research. She has been a part of BAS from a very long time, and she has been a really good friend with BAS. And whenever there are events at Indian Institute of Astrophysics, she has always invited us to volunteer and be a part of those programs. And we are really thankful that she is with us and she is sharing her knowledge and experience with us. And today's topic would be about the black hole photo that was recently published by the Event Horizon Telescope project. So thank you, Dr. Prajit Shastri. Over to you.
Uh, yeah, so thank you very much. It's a real pleasure and privilege to be part of this BAS series. My association with BAS goes back to basically the International Year of Astronomy, which was quite a watershed moment for many of us, and I sort of got to know many of BAS people and their work and so on, and we started to work together. And there has been no looking back. It's been a really very inspiring experience, I would say, to be able to work with the volunteers of the BAS. So when I actually have a confession to make. So when I discussed this topic with Kirti, and we arrived at this thing of how to photograph a black hole, it was actually before Ajay Talwar's talk last week, and then we had Ajay Talwar's talk, which was full of taking scopes out and f-stops and exposures and all the rest of that. And then at the end of it, someone announced the title of my talk, which is how to photograph a black hole. And I was in a bit of a shock because, as many of you know, almost by definition, one can't photograph a black hole. So my talk will not have any advisories on scopes and exposures and f-stops or any of that. And it's not, of course, like that you and me could take our scopes out and take a few time-lapse images and figure out how black holes move. But I do hope to convey to you the thrill of the collective endeavor, humanity's collective endeavor to understand black holes to their very depths. And so I'll begin with that. So photograph in this context is a bit of a metaphor. So I guess just give me a second. So are you able to see my presentation?
Not yet.
Okay, I guess I... So do I have to press share?
You have to select the present now, entire screen or
Yeah.
window, and then
And then
select that.
now?
Yes, it's loading.
Okay. So it's a real pleasure to segue from Ajay Talwar's talk in this fashion and have this photograph of the Milky Way as my background slide. It's a really favorite picture of mine, not least because Ajay Talwar took it and took it from while being perched on the Himalayas in India. So has the slide loaded fully?
Yes, it has loaded.
Okay, okay,
Yes, we can see now.
okay. So, hmm. Okay, so what are black holes? So black holes are chunks of space-time from which even light cannot escape. So when I say space-time, that's, I mean, I could say space, but space-time sounds fancy, but it's just a more complete description. So for example, if I say that I am here in my home in Bengaluru, that is true, but it is not a complete description because I have to say I'm here now. Only then it becomes a complete description. So that's sort of how you can think about what space-time means. So black holes are chunks of space-time from which even light cannot escape. So if you think about this concept of escape, I wanted to remind you of the concept of escape velocity, which we all learned about in our high school. So we know that if we throw something from the earth, because of the gravitational pull of the earth, that something will fall back to earth unless it is thrown with a rather large velocity. And that large velocity is roughly 11 kilometers a second. And what that velocity is depends on how heavy the object that is trying to escape from is. So in our case, from the earth. So there is this formula which we, all of us learned in high school, you might remember, which relates the mass m of the gravitating body, in this case, for example, the earth, the radius of that body, or rather how far you are from the center of that body, which is r, and the velocity v with which you need to launch that body if it needs to escape from this gravitational pull. Now, very early on, people try to imagine what it would be like if the body was so heavy that that even light would not escape. So this means that for instead of v, you put the velocity of light c. Are you seeing any progression in the slide? For some reason, I'm not able to.
We can see the picture of the Earth, and then we can see gm by r is equal to v squared by 2.
Right. And then why isn't it going ahead? Let me try
And now
that
we can see
again.
your entire screen.
Yeah, so but it says stop. It says I'm presenting. Oh, so I just need to go to play maybe and okay. So if you set the velocity, escape velocity to c, which is the velocity of light, then in the same formula, you get a relationship between m, which is the mass of the gravitating body, and r, which is how far you are from the center of that body. So that is all there is in this formula now. And the rest of it is the gravitational constant and the velocity of light. So you have a relationship between the mass and the size effectively. So what this means is that if you have a mass of a certain size, that if you squeeze it to a certain size, then if you squeeze it enough, even light cannot escape from this body. So this game I just played is purely with the classical physics formula, nothing fancy here. But it turns out that, and so this is this relationship between the size and the mass. It turns out that when Einstein proposed his theory of general relativity, one of the first solutions that was found to his equations was by Carl Schwarzschild, and that solution came out to be with the same formula that we just looked at earlier, by looking at escape velocity and equating that to the velocity of light. And so this is what is known as the Schwarzschild black hole. And although the formula does correspond to the classical case, it turns out that this object obviously is a relativistic object. It came out as a solution to Einstein's general relativistic equations, and so there are some consequences which are not quite intuitive. So this consequence that light cannot come out, that you can say is somewhat intuitive. One could sort of imagine that. One could imagine an object so compact that even light cannot escape from it, but there are other non-intuitive consequences. So, for example, I seem to have trouble going to the next slide. I don't know why. So for example, if you see this grid that I've shown in pink, which represents sort of a two-dimensional grid, if you have a mass at the center of that grid, which is represented by a sort of bright point, what Einstein's theory says is that if there's a mass there, that grid will curve.
Sorry to interrupt.
Yeah.
You have to represent again because somebody presented in between and they took over the presentation.
Oh, okay. So how?
Presentation and represent.
Sorry, what? I should go to the beginning?
You should go to the browser,
Huh.
stop the presentation and restart presenting again.
Oh, I see. Okay, maybe that's why I was having trouble. Okay, let me. So I'll start from, I don't have to start from the first
No,
slide.
you don't have to start from the beginning, just that we lost the screen that you were sharing.
Okay, understood.
Yeah, we were able to see your latest slide, which showed that two-dimensional grid, so you can just start from there.
Are you able to see?
Yes, it's loading, yeah.
So are you able to see that pink grid?
Yes, we can, yeah.
Okay. So, so what Einstein's general relativity predicts is that if you have a mass at some point, the whole space-time will curve, and that is represented here by this pink grid. So it's easier for us to imagine this in 2 dimensions, and that is why this grid is shown in 2 dimensions. This is kind of encapsulated by the famous statement by John Wheeler, which says, mass tells space-time how to curve. In reality, this happens in 3 dimensions. So we have to imagine a 3-dimensional grid, and we have to imagine that this 3-dimensional space will curve. So now the next point about this is, what does this formula tell us about what is the minimum mass of this kind of an object, which we call a black hole? Is there a minimum mass? Can there be electron-sized black holes? Are black holes seen in the laboratory? So the fact is that so far there is no evidence for black holes in the laboratory. There has been a lot of speculation about microblack holes and black holes of the size of an electron and so on. There's a lot of stuff on Wikipedia about that, and I won't go into that. But I will focus on actual real black holes. So the only black holes we actually know of are cosmic. And this idea came sort of quite a while ago in the earlier half of the 19th century, when Oppenheimer and Volkoff, this is the same famous Robert Oppenheimer. So Oppenheimer and Volkoff talked about how stars could collapse into black holes, and they brought black holes into the astrophysics context, and so black holes began to be seen as the end product of stellar evolution. So if you have stars which are heavy enough, then when they finally explored at the end of their lives, they could leave a remnant, which is a black hole. So if the remnant is more than about 3 times the mass of the sun, it will become a black hole. If it is lower than that, then it might become a white dwarf or a neutron star. And the theory is quite exact there. Exactly what mass of the remnant will result in a black hole is roughly 3. We don't have an exact value from theory. So how have we seen these black holes, and how can we see them? Before I go into that, I just wanted to remember a few people. So this is C.V. Vishweshwara, who was an astrophysicist who lived and worked in Bengaluru. And he taught many of us about black holes, and often he taught through his cartoons, which he drew himself. Quite a cartoonist he was. So he showed in 1970 in a paper which was called Stability of the Schwarzschild Metric that black holes are stable. So this is really essential for us to be able to see black holes. Another person, again, I'm having this trouble. Just one second. That I'd like to remember is my own PhD supervisor, Vijay Kapoor, who worked for many years at the TIFR. And one of his landmark results were he came up with strong empirical evidence for plasma outflows launched from the environment of black holes with bulk relativistic speeds. So that was very exciting. And of course, I would like to remember HN or H. Narasimhaya, a physicist from Bangalore, whose centenary we celebrated yesterday. I won't say more about him here, but it's a good moment to remember his contributions to not just physics, but physics education and society in general. Okay, so how can we see black holes? So black holes, as I said, curve space-time. I mean, any mass curves space-time, but because black holes are so compact, in the near vicinity of the black hole, the curvature will be very, very strong and palpable. So the two diagrams at the bottom are just two different ways of showing or representing this curvature. And what the diagram on the left shows, it has the sky background in the background and this grid which shows the curvature, and it is showing you that the light is kind of curved. So if space-time curves, then obviously a light will follow the path of that curvature. So normally light travels in straight lines, but in so-called flat space-time, if space curves, then the light will also curve. And this was in fact demonstrated by an experiment that happened in during the 1915 eclipse conducted by Eddington. So, for example, if we have such an image, and this on the left is a piece of the Milky Way, and let us say there is a black hole somewhere there, what we would expect to see is that because of the curvature of the space-time around this black hole, the light from the areas surrounding the black hole would be curved. So we would see something like this. So you will notice that where the black hole is, we will see nothing. It will be black as expected. But around it, we would see this background light, and the background light will be heavily distorted because the light will not travel in straight line. So this is sort of a silhouette of a black hole, and this is how, if we see something like this, that would be a sort of definite demonstration that there's a black hole there. But of course, this is heavily exaggerated, this picture that I've just shown you. By the way, I will be showing a lot of real images. I will also be showing diagrams and artist impressions and so on. And I will try and remember to point out what is real data and what is an artist impression. But please feel free to interrupt me if I forget to point that out.
Prajval, we have one. Can we have one question here?
Sure.
Yeah, so there was one question on the previous slide when you said that there were no laboratory evidence for black holes. But
Yes.
If it were to happen, so what will happen if a black hole is formed in the particle accelerator?
Yeah, actually, that answer to that question is outside my expertise. But it is true that they have looked for such black holes in the heavy accelerators that we have, like the Large Hadron Collider and so on. And I imagine that the kind of signatures would be similar to energetic particles. But I can't say more than that, because that's not, I mean, I'm a layperson, as I know as well as you do what the details are. So you have to ask someone else.
Okay.
But it won't definitely suck the Earth inside, right?
Sorry?
It won't suck the Earth inside it, right?
No. So first of all, no. So okay. So one thing that is known from theory, this is not demonstrated by experiment, but from theory, is that although I said that light cannot come out of a black hole and nothing can come out of a black hole and all of that, Stephen Hawking did show that there can be something called Hawking radiation, which is like a quantum effect. And so black holes can emit something called Hawking radiation. So the way the prediction is that the smaller the black hole, the more it will emit. And so these very, very, so the kind of black holes I will talk about, which are stellar mass black holes or heavier, in them, the amount of Hawking radiation is very, very low. So although you eventually expect that if a black hole emits Hawking radiation, it will eventually evaporate, the kind of black holes I will speak about will take an enormous time to evaporate. So we don't expect them to, change significantly within the lifetime of the universe. But if you have these very small black holes, because that because the amount of Hawking radiation is inversely proportional to the mass of the black hole, if you have these very tiny black holes, they are expected, shall we say, to emit Hawking radiation and very quickly evaporate. So their lifetime is also very small. So that is one point. The second point, and this is, of course, I should say, predicted by theory. This has not been demonstrated. The second thing is we know that the gravitational sphere of influence of a black hole is really, really small. If you remember these pictures I showed you, where are those pictures? So these diagrams which show you the curvature and so on, you can notice that the curvature happens only in the close vicinity of the object. So on this diagram is showing you the curvature due to the Earth, for example. And so that curvature is seen only in a very close vicinity. And as soon as you get a little bit away, space-time is kind of flat and normal. So the gravitational pull of the black hole is only in its close vicinity. So for example, tomorrow, if our sun were to turn into a black hole, it would make no difference to us gravitationally. We would, of course, stop seeing light and so on. That's different. But gravitationally, the way the sun kind of holds the solar system together by gravitationally driving all the planets, that would still continue as before. And the difference gravitationally, the difference we would see would only be if we went very, very close to the sun. So therefore, micro black holes following the Earth is not physical and not expected, even with the physics that we know. So does that answer the question?
Prajwal, can I just add one thing?
Yeah.
So yeah, during one of the Bangalore Science Forum's July lectures, there was a direct communication between a scientist from CERN and Bangalore Science Forum. So when I asked the same question, if they are going to see micro black holes at CERN whenever they have a run, so the response was that there were expectations, but even if at all they formed, like you were mentioning, the signatures would be very hard to distinguish, number one. Number two, even if they form, they would evaporate so quick that they might not even get registered by their sensors at the moment. So not sure if it still holds good. This was almost 8 years back or so, but I hope it still holds good.
No, there's nothing to worry about. I don't think so. So what you are saying sort of fits with what I recall, it is a fact that the theory predicts that they will evaporate very quickly. So if signatures have to be seen, they should be seen in that very, very short lifetime that these objects would have. But then again, that is theory, and that has not been demonstrated. Okay, so as I said, this is a very exaggerated view of what one might see, primarily because such a black hole would be extremely small in this large scheme of things, and so we would need an extremely, extremely sharp telescope in order to see this kind of an effect. And of course, we will return to that idea later in the talk. But how then have we been sure that black holes are real so far? So one method has been to use Keplerian physics. So as we know, gravitationally driven things are in Keplerian orbits. This is an example of the moon around the Earth and the Earth around the sun. Similarly, there can be two stars which are gravitationally bound to each other and in Keplerian orbits, and the law of gravitation gives us a relationship between the masses and the speed and the period of the orbit. So if you possibly had a black hole and another star gravitationally bound in such a system, then by measuring the speed and the period and by measuring the speed and the period, you could derive the mass, and you could then demonstrate that this is a black hole if its mass is larger than the value predicted by what is required by the relationship between the mass and the size. So you could check if the size satisfies this relationship of 2gm by c squared once you measure the mass. But I don't want to go into this method in great detail. It's a very interesting story in itself, and if I give another talk on the black hole mass ladder, then I will go into great detail. But suffice to say that about 65 such black holes are known now, and that is from direct measurement. And the estimates using stellar evolution theory and the structure of the Milky Way and so on is that there are about 10 million which are scattered all over the Milky Way. And these are the so-called stellar mass black holes. So they are of masses about 5 times or more the mass of our sun. So just a couple of digressions. So as astrophysicists, we use slightly different units because it's, there's things are too powerful and too massive and too big and all of those. So for luminosity or power, we tend to use the solar luminosity as a unit. So the sun's luminosity is about 4 into 10 to the power 26 watts, and we call that 1 L sol, or 1 L sun, and use that as a unit of power. Similarly, the unit of mass, we use the mass of the sun as a unit of mass, and the mass of the sun is about 2 into 10 to the power 30 kilograms. And that is what is M sun as a unit. Another digression I want to make is about false color pictures. So maybe most of you know what those are, but just to clarify. So here's a picture of a cat as we would normally see it. And to the right is an infrared picture of a cat. And to the right of that is another infrared picture of a cat. So what does it mean to have an infrared picture of the cat? Because we can't see infrared, right? So so this is just a representation of the data we get when we take an infrared picture of the cat, and it is not, the colors are not true colors. The colors just represent how much light is coming at that point. So the colors are in fact arbitrary, and so if you have such, we call it a false color picture because the color is not true. And if you have such a false color picture, it should be accompanied by a key, which is what these two images are showing, which tells you what color represents what intensity. Otherwise, a false color picture doesn't quite make sense. So the choice of colors is completely arbitrary and depends on the renderer. So here are just a couple of examples. Now, these two spiral galaxies, these are Hubble Space Telescope images, and they are so-called true color pictures, which means that the light as detected by the telescope from the red, the green, and the blue channels are mixed in such a way as to render a picture that would be roughly what the eye would see, given the eyes, our human eye's response to color. So those are referred to as true color pictures. And here's a picture of Uranus. These are both the same picture. On the left is a quote-unquote true color picture where you can see, you know, the sort of a limb darkening towards the top right, and the brightest part is slightly off-centered and so on. And on the right is a false color picture. It's the same picture, but it is represented as a false color picture with orange representing the highest intensity and white representing the lowest intensity, more correctly surface brightness, and you know, some colors in between. So that was a digression about false color pictures. I will be showing a lot of them because I'll be showing images not just in visible light but in other other frequencies as well. So I just said that we are able to find black holes if they are bound to another star using the idea of Keplerian orbits. Here is another such black hole that was found in the center of our Milky Way. So on the top left is a piece of the Milky Way photograph that I showed earlier around the center of the Milky Way. And the very center was imaged by this group in UCLA called the Galactic Center Group. There's also a group in Germany doing the same thing. So I will be showing an animation after this. So I want to explain exactly what this image is and then what the animation will be, and then I will let you see the animation. So in this image, you can see some multicolored splotches. So these are real data, and they represent stars. They represent infrared emission from a bunch of stars, which are there in the center of our Milky Way. And these have been given labels, you know, SO2 and so on. And then you see a star-shaped thing in the middle. This is not real data. It is, I wish it weren't a star. I wish they had used a cross or something to mark it, because a star makes it really confusing. But it is not a star. it just marks a certain position on this image, and you will see why this position particularly is interesting. And on the top, on the bottom right, you see the scale, 0.1 arc seconds. So the whole thing is roughly the scale of a parsec, or about 3 light years or so, the scale of the whole image. And on the top right, you see a counter. It's saying 1995. That is the date counter. So basically, what this group did is it took infrared images of the center of our galaxy at different times. And they did this for now almost 25 years. They started in 1995 and went on. I have the images until last year. And they put them together to make an animation so that we can see how these stars are moving, because with time the stars move. So the next slide will have that animation, and it will have all of these, the splotches, which are the real data, which are the actual stars. They will have the labels, and they will also have certain curves into the image, which are not real data, of course, but they are meant to guide the eye as to what's happening. So can you see this video? So can you see the video?
Yes, we can see.
Yes, we can see.
So can people see the video?
Yes, we can see that.
Yes, we can see.
Hello, Vishwa, can you see the video?
Yes, Prajval, we can see the video. We can see the video.
I think our audio is not able to hear our audio.
Yeah, we can see it.
Okay, and can you hear me? Because I can't hear you somehow.
Yes, it is audible.
Okay. All right. So the video is looping. So you can see up on the top right corner the date counter, and you can see that it is progressing from 1995 into the end of 2018. And what you can now notice, you can now see why the position of that white star is interesting, because you can see that all the stars are making sort of elliptical orbits with the position of that white star as a focus. Okay, so this clearly tells us that there is something there at the position of the white star, which is very massive. It is so massive that it is able to drive all these stars in elliptical orbits. Now, using the Keplerian formula, we can actually derive what this mass is, because we know the speed, and we know the size of the orbits. And there is some redundance as well, because there are all these different stars which are moving around that same point as the focus. Moreover, if you look at one particular star, which is star SO2, which is a yellow orbit, you notice that it is passing very close to this to this position of the position marked by the white star. And moreover, it's passing so close that it still emerges and continues along its same orbit. What this means is that it has not had a collision, or it has not been deflected by this dark object, which is driving gravitationally all the other objects. The same is true for the pale pink star, which is marked SO16. That also passes fairly close to this position, but emerges without any apparent collision. So what this means is that this massive object at the position of the white star, which is driving all these stars, it must be really small. It must be smaller than that distance between the yellow orbit and the white star. at closest approach and the distance between the pink orbit and the white star at closest approach. So by applying the Schwarzschild formula, it turns out that the mass here is 4 million solar masses. That is 4 million times the mass of our sun. And the size of it, it's not a size, but a limit on the size, right? We can only say that it must be smaller than whatever that distance is. So that clearly tells us that it must be a black hole. So what this experiment told us was something really important, that our Milky Way has a black hole in its center, which is 4 million times the mass of our sun. So this is a little different from what I said earlier about there being 10 million, roughly 10 million stellar mass black holes scattered all over the galaxy, because this has a mass of 1 million solar masses, 4 million solar masses. Okay, so this was a relatively recent experiment. I just saw the details, but we had circumstantial evidence for the existence of such giant black holes, and I will call black holes that are more than 1 million times the mass of the sun as giant black holes. Technically, they're called supermassive black holes, so I'll use both those terms. So we had circumstantial evidence for these from a very long time. So these, there's an example here that I'm showing you of an object in the sky which was known to flicker. That is, its light was known to vary at a variety of frequencies, including the optical. Here is shown the optical band. So there's a U, B, V, R, and I bands. And what is plotted is the brightness as a function of time. So you can see that these dots are going up and down, and so the brightness is not a constant with time. On the left are images of the piece of sky where this object is located. So the object of interest is at the center of these fields, and top to bottom, these are infrared, visible light, and at the very bottom is a visible light picture on top of which is superposed a radio image with contours. So it is this object, the central object, whose light curve, as we call it, is shown on the right side. Now, this allows us to use what is called the light travel time argument to infer what is the size of the region that is emitting this light. So I'll just explain that. So if you look at this diagram, and let's say you have an object which is spherical, represented by the gray circle, and let us say at some point in time it brightens for whatever reason. The two blue sort of wiggly arrows represent sort of photons that would come from this object to us who are behind that telescope like thing on the right. So what you can see is that obviously a photon coming from the far side of this yellow object, which is the wiggly arrow on top, would reach us later than the photon coming from the front side of the object. So therefore, when the object suddenly brightens, from left to right. So when the object was in the state where it's represented by the gray circle, it had a certain brightness, let's say. And then after some time, it brightened. So when it brightens, let us say it brightens instantaneously. We will not see the brightness increasing instantaneously because we will see the photons from the front side of this object first, and then the photons from the next layer and the next layer and so on, and the photons from the back layer would come to us last. So what was an instantaneous flare, to us it would be a kind of blurred out increase in brightness. And what would be the extent of that blurring? It would be the velocity of light. It would be that distance divided by the velocity of light. Distance meaning the size of the object. So the size of the object in our line of sight. Which means that by looking at the time scale over which the change happens, we are able to guess what the size of the object that is emitting this light is. So that is the cute thing about this light travel time argument. So of course, you can't do this by just one measurement. You have to have monitored it for a while and seen how the light changes with time, and then use that. But basically, the time domain gives us an insight into the spatial domain, even though we may not be able to take a very sharp image of this object and actually measure its shape and so forth. So for this particular object, for example, it turns out that the power that is emitted, the other thing, of course, is you need to know how far this object is. So in this particular case, we can determine how far it is using the expansion of the universe and the cosmological redshift. And so then we know how far it is, we know how bright it is, therefore we know how powerful it is. And from the fact that it has varied, using the light travel time argument, we know that it can't be bigger than some value. We don't know how big it is, but it must be smaller than this product of the velocity of light into the time over which it changed in brightness. So that gives us a size, and so it turns out that a huge amount of power, in this case, 1 trillion solar luminosities, that is power that is equivalent to 1 trillion suns, comes out of a region which in this case is a few light weeks in size or smaller. So that means that this enormous power coming out of such a small volume the only way to understand that and explain that was to posit that there is a very, very massive black hole there, and gravitational energy is being harnessed and is producing this power. Moreover, radio images of objects like this showed that there are these jets of plasma, twin jets of plasma that come out of the central region of these galaxies, and they are so powerful that the jets extend well outside the confines of the galaxy into intergalactic space. So this is an example of that. So what this picture shows is there is a true color picture in visible light, and that is showing you a lot of stars all over the place. But in the middle, there is this elliptical galaxy, a gravitationally bound bunch of stars. And from the center of this elliptical galaxy, there are these jets of plasma which are being spewed out. So this is a false color picture which is in pink and white and so on, which is overlaid on the true color picture in visible light, and the false color picture is taken at radio frequencies. So these twin jets, they are primarily seen at radio frequencies, and the reason is that I was just looking at a message. Okay, so can you just speak, somebody, Vishwanath?
Hi, Prajval.
Yes. Okay, I can hear you now. Yeah.
Okay.
Yeah. So I wasn't able to hear. I think I turned off my volume by mistake. So, yeah. So this pink image is a false color image taken at radio frequencies, and these kind of twin jets are easiest seen at radio frequencies. The reason for that is that this light is not coming from stars, right? The galaxy is emitting light because its stars are shining. And its stars are shining because of the usual phenomena, just like our sun. But these jets of plasma are shining because of so-called synchrotron emission. So this is light which comes out when you have a bunch of relativistic particles which are moving in a magnetic field. And that generates what we call synchrotron radiation. And this radiation, just the way it is most powerful at lower electromagnetic frequencies, and as you get to higher and higher electromagnetic frequencies, it gets fainter and fainter. So it's not as if you can't see it at other frequencies. So this is an example of a galaxy called Messier 87, and at the top left corner the galaxy is shown, that is all the stars of the galaxy, and that's also an elliptical galaxy. And if you look at the pictures below, the picture in blue is showing you one of these twin jets of plasma which is coming out of the center of the galaxy. To the right is the same jet but seen in visible light. So with a very, very sharp image, you can actually see this jet of plasma emitting synchrotron light. You cannot see this in the picture top left because it's simply not a sharp enough picture. But you can see it with the Hubble Space Telescope. And to the right of that, in a sort of purplish color, is the same jet seen in X-ray emission. So this synchrotron jet of plasma does emit at all frequencies, but as you go from lower to higher frequencies, it becomes fainter and fainter. And this is the reason why radio frequencies are the best frequency to see these plasma jets. And what the big picture on the top right, what that is showing you is that you can see the same jet that is shown in blue also in the big picture. I guess you can't see a cursor, right? Can you see a cursor on the screen?
Not visible.
Okay, doesn't matter. I'll just say it and I think you can understand. And if you don't understand, you please ask. So I'm trying to now explain the big picture that I put on the top right. And so here you can notice that in the middle, there is this jet of plasma that you see. It's again a false color picture, and it is the same picture that is shown in blue on the bottom left. So it's just a different rendering, different colors. And then you can see the top left, it is showing you a zoomed out picture. And you can see that, you know, these twin jets have reached really far out into the intergalactic space. And to the right, the picture that you see where the central part is reddish. So all these jets and this jet and so on is within that reddish patch. And you can see the really, really big lobe of plasma. And so that is again due to the same central powerhouse, but that is emission that happened much earlier, and so it has reached out much further. So is that understood? Shall I go ahead? Or are there any questions about this?
I have one question here. So
Sure.
we only see one jet. So there should be another opposite jet in the direction opposite to this particular jet. Can we see that, or do we need something special to see the other jet?
Yeah, so that's a very good question. And in fact, maybe I'll come back to that in a second, okay? I'll show you the next picture. So just by looking at that picture that I showed you, it's not obvious that this plasma is originating in the center and then moving out, because you might ask how do you know that? How do you know it's not plasma that's generated outside and is moving inwards into the galaxy and then plunging into the black hole? So the reason is that if you really, really zoom in and measure this plasma jet, then you can see, and people have done this, and people have done this at different times, and they have done an animation to see whether there are any changes, and this is the result of that animation. So in this slide, on the top, on the top left corner is something called the Very Large Array, which is a telescope used to make these the image which I showed you already of Hercules A, the pink colored twin jets. And then the rest of this slide has another galaxy called 3C120. The image on top is showing you a similar jet. And at the bottom, in green, is in a green square, within a green square, is this image very, very zoomed in to the very center. So in the top image, which says 3C120 from 1 arc seconds to 3 arc seconds, at the bottom left, you will see sort of a bluish looking thing called the core, which I'm saying is where this jet of plasma starts. So if you zoom in within that blue area, what you see is shown in the green square at the bottom. And I'll try to see if this animation works. Yeah, so now you can see that there is stuff coming out and moving outwards, right? It's moving down and right. It's telling us directly, so we are actually able to see that this plasma is moving, it is originating in the center of the galaxy, and it is moving outwards. It is moving outwards not randomly, but in a highly collimated beam-like structure. And now to come to your question, where is the, shouldn't it be two? Where is the second one? Because in the pink image of Hercules A, you can actually see two jets. The reason is as follows. The speed at which this jet, this plasma is coming out, turns out to be almost the speed of light. We call it relativistic, which means that it is over 90% the speed of light. So when that happens, there is an optical illusion that occurs. Because the photons, the plasma is almost traveling at the speed of the photons that it itself is emitting. So as a result, it is heavily relativistically Doppler boosted towards us. So it's heavily blue shifted, and blue shifted means higher energy. So we see more power than it is actually emitting, simply because it is emitting it at relativistic speeds very close to our line of sight. So the plasma itself is almost keeping up with the photons that it is emitting. Now, for the plasma that is going in the opposite direction, it is the opposite is happening. So it is going away from us. So it will be Doppler redshifted, and it will be therefore dimmed. So it is so dimmed that in this picture, this image that I'm showing you, the so-called dynamic range of the picture is not very high. That is, the ratio of the brightest thing this picture this measurement can see to the faintest thing this measurement can see is not very high. And so the faintest thing drops out. So the opposite jet of plasma drops out of the image. It's not that it's not there. It is, this image is not does not have the dynamic range. So it's not about sensitivity, you know, it's more about dynamic range. Dynamic range means, you know, like when you're walking at night and you have a car coming at you, the light beams of the car blind you to the stuff around you that you were otherwise able to see. So it's not about sensitivity. Your eyes are sensitive to see some things in the dark, but when the car light beam blinds you, you're not able to see. So in the presence of a bright object, you're not able to see faint things. That's called dynamic range. That's the jargon term for it. And so because of the dynamic range limitation, you're not able to see the opposite jet. Did that explain?
Yeah, it does.
Okay. So how does this happen? So this is a, I'll try to see if the simulation plays, otherwise I might ask Vishwanath to play it separately. This is a computer simulation that takes into account, that is so-called general relativistic magnetohydrodynamic simulation, which is just a fancy way of saying that if you take into account the mass of the black hole in the center of the galaxy, the fact that it's a general relativistic object, so general relativistic physics operates in the near vicinity of this black hole, and there is this stuff around the black hole which is getting pulled by the black hole and therefore spirals into the black hole, but in the process is heated to very, very high temperatures. So it's a plasma. And because it's a plasma, there is, the special things that happen within plasma fluids applies. And because it's a plasma, magnetic fields are generated, which will again have an impact on the physics. So all of this put together, this group of researchers has created a simulation. So this is not real data, this is a simulation, and it shows what might happen. So in the simulation, the stuff that is the plasma is represented by sort of yellow, red, and green colors. And the animation didn't work. So I'll exit out of this, and Vishwanath, if you could please play that simulation which was called McKinney something.
Yes, I'll play. One sec.
Okay, so do I need to do anything? Do I need to say stop sharing or something?
No, not required. I'll share I'll share my screen. So once I have done, you have to again stop present and represent.
Okay, and while you're doing, can you still hear what I'm saying?
Yeah, we can.
Okay, so this while we're waiting for Vishwanath to show that simulation, the simulation will have some sharp green lines, and they are meant to represent the magnetic fields that are generated in this process. So just imagine that you have this black hole. It's of course has huge gravitational pull. Any matter which is coming near it is pulled into the black hole, so it spirals into the black hole, which you can also see in the simulation, and in the process gets heated to a plasma that generates magnetic fields. And this in the process, most of the material does plunge into the black hole, but some of the material gets spewed out in these beams of plasma, which is what we saw earlier. So the simulation just shows that it is possible to generate such beams of plasma.
Okay.
So did everybody see that? So you see how the green lines, which are the magnetic field lines, how they are twisted around and spiral, and as a consequence, they generate these beams of plasma, which is the blue stuff, which is coming out of this system rather than plunging into the black hole. Okay. Yeah, you can stop it now, I think. So now what do I need to do?
You just have to represent the screen.
So I just need to click on the presentation.
Stop presentation and start presentation.
Hello, can I ask a question?
Yeah, sure.
Hello, ma'am. So I wanted to know if the black hole is a rotating one or a stationary one in that simulation. Thank you.
So, yeah, that's a good question. So in the simulation, it is a rotating one. So if you have a stationary black hole, I mean, I don't know of any simulations which have been done with which non-rotating black holes. So it is possible to generate some sort of outflow even without the black hole spinning, but the kind of highly collimated, very narrow beams and so on. And we do know, we have actually measured magnetic fields in these beams of plasma. So generating such do require a rotating black hole.
Thank you.
Okay, so now I want to go to the question of how do we actually make
Prajval,
these? Yeah, sure.
You have to do the representation. We don't see your slides.
Oh, okay.
Yes.
Now?
Yes, I can see now. Yeah.
Okay. So how do we actually do this imaging? Because as I said, this is synchrotron emission, and it is very hard to see it in visible light or X-ray light or something. It's most easily seen at radio frequencies. But the thing with radio frequencies is that the frequency is much larger than the frequency of visible light. And as you know, we need sharp images. Now, the sharpness of an image that we can make with the telescope depends both on the size of the telescope. So the larger the telescope, the sharper the image. And it depends on the frequency of the telescope. So the higher the frequency, the sharper the image. Or the higher the wavelength, the lesser the sharpness. So radio frequencies are much lower. As you know, the wavelengths are typically a few to meters. And so the resolution is quite low, and so to get comparable resolution, comparable sharpness to a visible light image, you would really need a very, very big telescope. Now, on the slide on the left is a telescope, one of the telescopes of the Giant Meter Wave Radio Telescope in Maharashtra, which is run by the Tata Institute of Fundamental. And if you look at this dish, it's rather large. It's a 45-meter diameter. So the detector is at the focus of this dish. Now, typically in these radio telescopes, there is only one detector, which is sort of like having a CCD with just one pixel at the focus of a telescope. So then that is not an imager, right? Because if you want to do imaging, you need to be able to detect emission from a bunch of different directions around the central direction where you're pointing. So with a CCD, it's of course very easy. You have an array of pixels. Each of those pixels is responding to a slightly different direction, and that's how you have an image of whatever piece of sky or face or scenery that you're looking at. Now, in a radio telescope, that's really hard because you typically have only a single feed or dipole or circular feed, and if you were to make an array of detectors, just like you have, so the feed is equivalent to one single pixel on a CCD, and if you were to make an array in order to image, you can see that it will become really big and it will start to obscure a lot of the photon collecting area. So on the right is another example. This is the so-called Effelsberg telescope. It's one of the largest steerable telescopes we have. It's a diameter of 100 meters. It's in Germany, and so the resolution of this is about an arc minute at a centimeter wavelength. That's like the resolution or sharpness of the human eye. So that's not great at all. And if you were to increase, if you were to replace the single feed with an array, then you would obscure a lot of the region that you have. So as it is with the single feed, it's not just that it's not sharp enough, it is not an imaging instrument. So if you wanted to have it as an imaging instrument, you would have to have this array, and you would have to make the dish itself much, much bigger. And there is a mechanical limit to how big a dish we can construct. So getting sharp images with a single radio telescope is really a pain. I mean, you could do a sort of a raster scan of the sky and take images. You take image of a point, then shift the telescope, then take an image of that and shift it and so on, and then that way construct an image of a piece of sky, but then you wouldn't have done it simultaneously. So if something changed in the first measurement you made, by the time you were halfway through, then that's not going to give you a very good result, and so forth. So but there has been a way around this, and this has been known for a long time, and that is using the idea of interferometry. So how this works is, so here is this pale blue circle, which is, let us say, our dream telescope. So ideally, we would want this big radio telescope to get the sharp images we want. But we can't build such a telescope. So instead of building this big telescope, let us say we just build two pieces of it, which are represented by the two dark blue circles. Now we combine what each of these sees, but combine is not adding, because by simply adding, all we will do is increase the total, effectively the total number of photons we've detected. Not adding, but so-called correlating. Now correlating means that you stop thinking of light as rays or photons or particles, but think of light as a wave, and therefore it has both an amplitude and a phase. And you add the signals from these two. So remember, the pale blue thing doesn't exist. That's in our imagination. That's our dream, right? What we have is the dark blue, the two dark blue things. So we take the output from these dark blue things and correlate them. That is, we take into account both the amplitude and the phase of the light wave that they're seeing. So this is sort of like doing a double slit experiment, or it's sort of like if you were at the sitting at the edge of a pond of water, and you created ripples in the water with two of your hands, and you watched how the ripples then interact with each other. And you would notice that there are places where the ripples constructively add, so you get a trough or a crest, and then there are places where they destructively add, where you get nothing. So this is the principle that is used in this case. And the point to remember is that if you correlate the output from these two things like that, you are not getting an image of the sky. You are actually measuring one component of the Fourier transform of the sky. So just to introduce that idea, here is shown on the top a curve which is sort of, you can take it to be sound, let's say. So it's the amplitude of the sound plotted with time, and there is a wavy pattern to this. You can see that it's sort of periodic, but it's not a simple wave. Now we know from our what we've learned in high school about Fourier decomposition that this kind of a wave can be represented as the sum of a bunch of very simple waves. So that is what is shown at the bottom. So the top, if the top can be reproduced if you add all the waves at the bottom. But they have to be added not with equal amplitude, but with differing amplitude. So you can see that the green wave, which is somewhat higher, which is somewhat lower frequency, is somewhat high amplitude. And the purple wave is very, very low frequency. It's barely varying. It almost looks like a straight line, but it's very low amplitude, and so on. So by adding all these waves, you're able to produce the wave on top. And what is shown at the bottom is this same decomposition, but plotted in a different with different axes. So the left axis is the same, the y-axis is the same as on top, but the x-axis is now frequency instead of time, and it is showing you the 4 different waves that need to be added in order to reproduce the thing on top. And each of these is, you can think of as one Fourier component of this wave. Okay, so this is the wave that is shown here in purple on top is a relatively simple pattern. You can imagine that there are more complicated patterns than that. And further, you have to now transform in your mind from a single dimension to 2 dimensions, because the sky is a 2-dimensional object we are trying to image. So there are wave-like patterns in the sky. So you think of the structures in the sky as sort of how can we build the structures in the sky as a sum of different wave-like patterns. So that would be the Fourier decomposition of the image. And a combination of 2 telescopes, like the way I described earlier, would measure one of those components. So it would be like it measures one of these 4 frequencies shown here. Now, obviously, if that's not very exciting to just have one Fourier component of the image of the sky, because that, what do you do with that, right? But if you had more telescopes, so now you're not limited by your mechanical constraint. You're constructing relatively small telescopes. You're scattering them along this big dream telescope, and then you create pairs between these. So you can imagine that each of them would measure a different Fourier component of the image of the Fourier transform of the sky. So by increasing them to a large number, you can imagine that you would be able to measure more and more of the Fourier components of the Fourier transform of the sky, and then you could Fourier transform them back to reproduce the actual image. Now, that is what is attempted in, for example, the Giant Meter Wave Telescope in Maharashtra. It is not a single, it is an array of 30 different telescopes. And that was the same with the other telescopes that I showed you earlier. Now, there is one more point to this, which is very interesting, that we can use the Earth's rotation to increase the number of Fourier components that we measure. Because as you can imagine, if we are only measuring the Fourier components of the Fourier transform of the sky, the more components we measure, the better we will be able to then reverse that operation and obtain the actual image. So here is shown the Earth. See, look at the top diagram, and certain radio telescopes, which are real radio telescopes at different places in the sky. Most of them are in Europe, and then a couple in the US. And you can see that the Earth is shown to be rotating as you go from left to right, and you can see more and more of these telescopes. Now imagine that you looking at the Earth like this, you are at the position of the star or galaxy or whatever that one is trying to image. So then what will happen is, when the Earth is in the position that is at the left, you take a pair of these radio telescopes, which I have marked in orange in the bottom panel. So the line between this pair, it is changing in both length and in orientation as the Earth is rotating, right? Because what I'm seeing is a sort of a projection in the plane, in the two-dimensional plane of what is a three-dimensional Earth, and these two telescopes placed on that three-dimensional Earth. So in the left, the projected line between these two orange circles, which represent two of the telescopes, is of a certain length. The projected line is of a certain length and a certain orientation. And then when the Earth has rotated a little bit, the orientation has changed quite a bit. The length has increased because now the projected distance is different. And then on the right, again, the orientation has changed to the sort of opposite orientation, and the distance between has reduced. Now, the point is that at each of these positions, the pair of telescopes has a different projection, both in orientation and in separation. And so if you make a measurement at each of these instances, you're measuring a different Fourier component. So in other words, if you use such a pair to continuously look at an object, then at each instant you're measuring, you're accumulating a whole bunch of Fourier components. So that helps the image, and the image, when you do the reverse transform, the image becomes a nicer one. So this is a technique that is used to create images at radio frequencies. And in the top left is shown something called the Very Large Array, which is similar to the Giant Meter Wave Telescope in Maharashtra, but the frequencies are different, the size of the telescopes are different, and so on. But the principle is the same. And the interesting thing is that, so although this sort of a telescope is what was used to create this image of Hercules A, which is shown in pink, the images shown in within the green rectangle, they were obtained by separating these telescopes even more. So as you can imagine, the larger the separation between these telescopes, which are used to simulate a bigger telescope, the sharper your image. So by separating these telescopes by a whole continent, one is able to increase the sharpness of the image enormously, and that is how we get this really this ability to really zoom in to the very, very vicinity of the black hole. So now I will talk about the recent Event Horizon Telescope, and the principle it used was the same. But why was it? Was it optimistic to image the silhouette of the black hole? So basically, let me go back a little bit and say that I showed. So in this slide at the bottom right, what you're seeing is an image I showed earlier, which is not a real image, but a prediction of what we would see if there was a black hole, and if we were able to take a sharp enough image where we saw how the light around the black hole is distorted, but the black hole itself is looking black, so we would be able to image the silhouette of the black hole. Now let us shift to these giant black holes that I already spoke about, which create these jets of plasma and which have material moving around them and spiraling into them at very hot temperatures and so on. This material that is spiraling into the black hole is at very hot temperatures and therefore shines, and therefore we are able to see that material. And that is what is represented in the image here in the top left. Now, this is not a real image. This is just an artist impression. But what it is showing you is material spiraling in to some central dark object. Now, if this were an ordinary dark object, this is what you would see. But if it's a black hole, there is something really special that is happening, and that is shown in the image which I've pinched from the movie Interstellar. This is Gargantua in the movie Interstellar, where there was a simulation shown, if you remember, in the movie. And the actual physical thing that is happening is not different from what is happening in the upper diagram. But because this is a black hole, and because the black hole curves light, the light from the backside of the black hole is also seen, because it is bent by the black hole to give this sort of a hat shape to the kind of emission that we see. Similarly, some of that emission is curved by the bottom half of the black hole, and you get this sort of circular shape around the black hole. What does this mean? This means that if you have this lot of stuff which is spiraling into the black hole and very hot and therefore shining, you will get a silhouette of the black hole with much heavier contrast compared to this image that I've shown at the bottom right. Because the image that I've shown at the bottom right, the only background light there is all the light from the sky, from the different stars and so on. But on the other hand, if you have this black hole which has stuff spiraling into it and therefore shining, you will get a silhouette with much higher contrast. So this is what gave hope to be able to detect the silhouette of the black hole. The instrument used was the Event Horizon Telescope. The principle used was the same that I described earlier, which is the principle of interferometry. And these are the different telescopes. They are located in these different spots, which is shown on the map here. So they are labeled SMT, LMT, Apex, ALMA, etc. ALMA was the biggest of them, the Atacama Large Millimeter Array. At the South Pole, there's a telescope called the South Pole Telescope, and so on. So all of these telescopes were used in an array. So each pair was used as the way I described earlier. The output from each pair was correlated, all of these things put together, and then the Fourier transform done to get us the actual image. Now, the two objects, there were many objects that were chosen. The most promising was this object that I've showed you earlier, which is Messier 87. I just realized that my laptop is running out of battery. I didn't expect this to happen. So just give me a second. I'll put the battery and I'll be back. Charger and I'll be back. Can you hear me?
Yes, we can.
Yeah. Okay. So the most promising among all the candidates chosen for this kind of image was this galaxy called Messier 87. So I showed you before, but this is just to give you a sense of where it is. It's in the constellation Virgo, and so that is Messier 87 there in relation to Spica in the sky. And these are the images I showed you earlier. So on top left is the galaxy itself, which is all the stars in the galaxy shining. And on the right is the radio image. And this was known earlier. So what the Event Horizon Telescope is trying to do is to zoom really, really in. So if you look at this blue image, which is the radio image taken with a very large array, that Y-shaped telescope I showed you earlier, the Event Horizon Telescope is zooming into that white circle that you see there. This is just a different false color image rendering, which also shows the scale. So it's the same image as before, except it's rendered in orange and so on. And you can see the white patch in the center, sort of a pear-shaped patch, and that is where that jet of plasma is. And zooming into that by a huge amount is the Event Horizon Telescope image, and this is what they saw. So this was the iconic image, which many of you have probably seen before, the image on the bottom right corner. So what this is showing, first of all, it's showing what was expected. So there is this shining ring, which represents this very hot material that is spiraling into the black hole. And then it is showing the silhouette of the black hole itself. So compared to all the circumstantial evidence that we had in the past, that I talked about with these jets of plasma and moving at relativistic speeds and so on, and the actual measurement of the mass of the dark object and a limit on the size at the center of our Milky Way, which tells us there is a giant black hole there, and all the stellar mass black holes that have been, whose mass has been measured all across the galaxy, this measurement, and of course I shouldn't forget the LIGO measurement, which also happened, where there was a very definitive measurement of the masses of the two black holes that merged. This is, in a sense, the most direct image of a black hole. This is as direct as you can get. You can't get more direct than this because the black hole doesn't emit any light. And so the most direct you can get is to measure the silhouette of the black hole. So this is a larger version of that, and the measured mass, this was known earlier that it was 6 billion solar masses. This was confirmed by the Event Horizon Telescope result. It was known earlier that it was roughly that. Yeah, so the Event Horizon Telescope made this observation in 2017. And as you can imagine, it was a very, very complicated data analysis project, because you have all these different baselines, and then each of them is measuring a Fourier component. Oh yeah, what I forgot to mention, this was important. The reason why it became possible to measure the silhouette with this region, with this of Messier 87 black hole, is that first of all, I said earlier that the larger your telescope, the sharper the image. So here you did have a very large quote unquote telescope. So the largeness here is the maximum distance between any two. So that is how sharp an image can get. But moreover, the frequency, and I said that earlier as well, that the higher the frequency, the sharper the image. So this frequency was 1.3, was a few hundred gigahertz. So that is the same as 1.3 millimeters. So this was the first time such a experiment was done, where interferometry was done at such a high frequency with such a large, we call it baseline, meaning distance between telescopes that were used. And this is the reason for achieving this very high resolution and being able to zoom in to measure the silhouette of a black hole. So this happened, and the observations happened in 2017. It took quite a while to do the data analysis. It was a very complicated data analysis process. They have also looked at the Milky Way black hole, but they haven't released the images yet. There it's going to be more difficult, because there isn't that much of material which is spiraling into the Milky Way black hole. So you don't have that advantage of this high contrast that you have here with Messier 87. And also it is quite likely that the whatever little shining is there, it is changing on the time scale of it's changing on the time scale of the measurement itself, which would be over a night. So that would complicate the analysis further. But they have data on the Milky Way giant black hole, and we do hope to see some of those results soon. They have released one other. They have released data on one other galaxy, but that is the galaxy which has these very, very powerful twin jets of plasma, which are very, very relativistic and very close to our line of sight. So there they have seen the base of the jet of the plasma, but they haven't actually seen the silhouette of the black hole, because the black hole is probably not in the line of sight in that case. So I think I'll stop here and I'll take questions.
Hello, hi. I have a question. So, in that image of the black hole, we see that there are some knots at the bottom. That means there are some brighter areas at the bottom, and the top half is not as bright as the bottom half. So, so why is that, and why do we have these knots, like some brighter areas?
Yeah, so that is also not actually surprising. So when you have this stuff, so if you remember Gargantua, for example here, so this is, you can see here also that one side of this stuff that is spiraling in is brighter, the left side is is brighter compared to the right side. So the left side is also slightly bluer compared to the right side. The reason for this is if stuff is spiraling in, then on the left, the stuff is moving towards us. And then in the middle, the stuff is moving across our line of sight. And then in the right, the stuff is moving away from us. Right? So we would expect that the stuff that is moving towards us will be blue shifted, and this will be relativistically blue shifted, and therefore it will be of higher power. We will see it to be of higher power than it actually is. So it's shining material because it's hot, and it is moving towards us. So we will see it of higher luminosity. Whereas the stuff on the right is moving away from us. So we will see the opposite effect. We will see a dimming of the power that it is actually emitting. And so this is what how the image here is interpreted, that this material is moving, this part of it is moving towards our line of sight, and so is brightened, and the other stuff is moving away from our line of sight, and therefore it's darkened.
Okay. And the material which is spinning around this black hole, is it in the form of a disk, or is it like a sphere which is covering the whole black hole? Um, so what I mean.
No, I understand what you're saying. So it is believed to be in the form of a disk. So one thing is, theoretically, it was always posited that it was in the form of a disk. I mean, both things have been discussed in the literature. So in principle, you could have stuff from all over, plunging into the black hole, and that has a name. It's called Bondi accretion. It was I guess first discussed by Hermann Bondi, who was an astrophysicist, so it's not, physics doesn't rule that out, but there are a lot of different pieces of evidence which favor the idea that it is a disk. And if it, in this particular case, Messier 87, if it had been spherical, then we wouldn't see the silhouette of the black hole, right? So.
Okay. Yeah, that's right. Yeah. Thank you. So if we were looking at it from a different point of view, so then would it look different?
How do you mean? No, so there is stuff all around, that this thing is sitting inside the galaxy, and there's stuff there and all that. So that could affect what we see. But here we're zooming in on this very inner emission. So for example, I mentioned the jets, right? So suppose we were looking, so Messier 87 jet is not that close to our line of sight. So it's not coming at us directly.
Okay.
If it were coming at us directly, then we may not be able to see this kind of a very clear silhouette and so on. So in that sense, yeah, the orientation would matter, but it would matter because of the stuff around, not because of the black hole, the black hole itself. Okay. Of course, if the disk around the black hole, like in Gargantua, the sort of spiraling in is happening edge on, right?
Yeah.
If the spiraling in was happening face on, that is, if our line of sight was such that we saw the spiraling in face on, then we would see maybe a slightly different, something slightly different quantitatively, but qualitatively it wouldn't be terribly different.
Okay, thanks.
I have one question. So here we, from what I understand, is if there is a lot of material around a black hole, so then it would make a much better contrast appearance when we do analyze the image. So quasars usually have a very active core, and they have huge materials falling in through the black hole. Suppose if we were to do an analysis on a quasar, so wouldn't it look much better than this, or how would it would look?
Yeah, so yeah, it's a trade-off between the size and this contrast. So you're absolutely right that accreting black holes stand a better chance of being seen because they would offer much higher contrast. And quasars are accreting black holes with billions of solar mass black holes. So in that sense, yes, they would offer higher contrast. But then on the other hand, they are much, much further away. And the further away it is, the smaller is the size of the black hole, apparent size of the black hole. So very low mass black holes would also be small because because of the formula, right? The relationship between mass and size. So small black holes would be small mass black holes would be small, and large mass black holes would be preferable. But then if the large mass black holes are too far away, they would also be small, as in not in physical size, but in angular size. That is in the size, apparent size for us. And for sharpness, what matters is the angular size. So there is this sweet spot, where of distance and mass, and the Messier 87 fitted that beautifully. So it is a very massive black hole, several billion solar masses, but yet it is close enough that the angular size was amenable to measurement by the Event Horizon Telescope. There are not that many objects like that.
Yeah, thank you. Makes sense. Yeah.
Ma'am, as you said now, the smaller the size, the mass of black hole is that small. So just an question came to my mind is, hello, am I audible?
Yes, yes. Go ahead.
Yeah. So just like a neutron star, and it is small in size, but it is so dense that the gravity is very high there. So that cannot be a case here that a small black hole with high density can be very large at gravity, like gravitational pull, than a larger black hole. Does size matters in black hole? I mean that.
Okay, so I'm not sure I understood your question, but so if you look at the gravitational force outside the black, if you're asking about the force of gravity just outside the black hole, it is true that the tidal effects that will be there. And by tidal force, I mean, there is if you have an object with a finite size, then the point of the object that is closer to the black hole will face a stronger gravitational force than the other end of that object, which is slightly away from the black hole, right? And this difference would disrupt the object. You've heard the idea of spaghettification.
Yeah.
So that will happen more in a smaller mass black hole because the tidal effect will be larger. So for example, in these giant black holes with a million solar masses and above, the tidal effects at the surface or close to the surface of the black hole is not that high. So that's how in Gargantua, in Interstellar, this person is able to go close to the black hole and so on, because that black hole is more than a million solar masses black hole. So you mentioned density. So it's not clear whether the concept of density is valid or not, and it's outside my area of expertise to talk about what happens inside the black hole. But if you take density to be defined the way we normally define it, which is like the ratio of the mass to the volume, then if you calculate the so-called density, that is, if you calculate the ratio of the mass to the volume, the larger the mass of the black hole, the lower the density comes out to be.
Yeah.
Right, because the volume is also dependent on the mass, because it's dependent on the size. So if you work it out, that so-called density, I don't know if that density has any meaning or not. That you have to ask someone else who studies the interiors of black holes and all that. But and that's all speculative because we haven't actually been able to measure inside a black hole or anything. But if you do that, the density comes out to be less the bigger the mass of the black hole. So in fact, for these giant black holes, sort of facetiously, if someone asks the question, what is it like inside the black hole? The answer might be, well, just look out of your window, because that is the kind of density that comes out.
Yeah, got it. Thank you.
So when we say the size of the black hole, is it the size of the event horizon?
Yes.
Okay, all right, thanks.
I have one more question here. So
Hmm.
now, what is the future? So now we are able to combine the telescopes from one end of that to another one and take images at a much impressive resolution. So in the future, what all improvements can be done to scale up to increase more resolution? Are there any other targets that we might be interested in to take such fantastic pictures?
Okay, so the second part of your question, are there more targets? Yes. In the 2017 observing run itself, they observed several targets, including the Milky Way, and there's this other object called 3C279, which I said has a very, very relativistic twin jets. So that they have just published the results for, and they observed many others, and I'm sure they will all be giving interesting results. Not all of them did measure the silhouette of the black hole, because as I said before, some conditions have to be good for that. But they definitely have a lot of measurements, and they will probably improve upon their analysis techniques, and also they can increase. So, but with that particular array, they can't do much about increasing the sensitivity, because it's what we have already, the telescopes that are existing already. But there is a way to improve resolution. This is a bit futuristic, but you probably heard of Radastron, the Russian satellite. So this is a radio telescope that has been put on a spacecraft. And so that increases the baseline, right? Because in the Event Horizon telescope, you're limited by the size of the Earth. You can't have a baseline which is beyond that, and therefore at a given frequency, that is as sharp as you can get. But if you put one of the telescopes in space, then you've increased the baseline further, and therefore the sharpness. Radastron was not operating at millimeter frequencies, so it cannot be added to the Event Horizon telescope. But in the future, there could be millimeter wave telescopes that are launched into outer space, and then you create a baseline with the existing Event Horizon telescopes that would increase the sharpness even further. So then, you could do more things.
So since the Earth is revolving around the sun, so can we take measurements over a period of time and make the telescope much bigger?
No, I mean, so you can take measurements over time over a single night. So if you remember the Earth rotation advantage that I described, right, where the baseline,
Yes.
as projected onto the sky, changes in length. So then, you're sampling different Fourier components of the Fourier transform of the sky. So if you do a full night like that, then you get a lot more Fourier components, and then you could increase it. But using the Earth rotation around the sun, unless you have one of the telescopes in space, it wouldn't make a difference, because you are not changing the distance between two of the elements of the array.
Okay, got it. But what I meant is, so there is this telescope which is moving in space. So if we um, I mean, I don't know. Maybe it's impossible, but if we take one measurement at this point of time, take another measurement 6 months later, and try to correlate them, then probably the size of this telescope would be as big as the diameter of the orbit of Earth's orbit around the sun. So,
Oh, that way. No, no. That would mean correlating. Yeah,
Temporal
no.
separation kicks in, right? If I'm not wrong. There's a
No, so
temporal
that would
separation.
be, yeah. So I don't know. That has.
It'll be at two different points in time, right? It has to be at the same point,
Yeah,
if
it
I'm not
will
wrong.
be. No, it has to be at the same time only because things may change. No, these objects are highly varying. If they were not varying, by varying I mean the accretion itself, that is the stuff spinning into the black hole, that is happening on scales of years or months and so on. So that will change. There are instabilities which develop in that flow, and that leads to some flares and so on, which are actually measured. And then I showed you the jet of plasma coming out, right? I showed you that animation. So that also, there are changes in the brightness. So if there are changes in the brightness, you would not want to, that will definitely mess up your analysis. And yeah, so you wouldn't be able to correlate that way. There would be other complications. Yeah, I don't think
got
that's,
it. So
yeah.
all the measurements have to be relatively fast, probably within one night or something
Yeah,
like that. So,
generally,
okay.
yeah.
Thanks.
Should I be looking at the chat window? I'm still.
Yes,
Vishwa,
there
can you check if there are any questions on the chat
yes,
window?
yes.
I lost
There are a
my
few
chat.
questions, so I'll start from earlier. Okay, one sec. So
So somebody said audio is not audible. So was there anything that I said that got missed or something?
no, no. I think those were temporary issues, and we could hear you
Okay.
almost entire session. So there was one question asked earlier. So in the animation of the central Milky Way black hole, the stars revolving around it. So there was one particular star S017 that appeared to go in a straight line rather than elliptical. So what could be the reason for that, or was it anything on that particular star?
So are you able to see the animation?
Yes.
Okay, so the yellow one is this star which is labeled SO2 and it's in an elliptical orbit.
The S017. The one which went
S017
bottom
is.
to top.
I think is SO16.
No, it's 17. The one in the
Okay, I'll go
light
back
green.
to 17. Okay, that is 17. Okay. Oh, I see. So yeah, so this is a star that is far away. So it's in this whole time period. That is all the orbit that is covered. its whole orbit has not been covered, and it sort of looks like a straight line because it's the plane of its orbit is probably close to our line of sight.
Okay. So there is one more question. So are radio emissions from pulsars generated by the same phenomena that generate jets from active galactic nuclei?
No, it's a very nice question, but no.
Okay. Do we detect pulsars from AGNs in the same way we do from pulsars due to them spinning?
No, so the mechanism in pulsars is different. I'm not a pulsar expert, but it's not, as far as I know, it's not an easy mechanism to understand. But it is very, very precise. So it is a continuous beam that is emitted, and because the pulsar rotation is very precise, the pulsations are very precise. So there are, it's like they're like clocks, and so that's a very different phenomenon. Whereas here, it is a consequence of this the curvature of space-time and matter spinning, spiraling into the black hole in this curved space-time, and being accelerated and heated to very high temperatures and becoming a plasma, and therefore generating magnetic fields. And then, as you saw, there are these magnetic fields which are generated perpendicular to this disk of spinning stuff. And then because of the disk spinning, those magnetic fields are getting twisted. And then those generate the twin beams. So yeah, so in that sense, this is very different. What does happen is that if this beam of plasma is very close to our line of sight, then if there are some shocks or something moving in it, it could be that we see brightening and dimming because they are within our line of sight and then go out of our line of sight and then again come into the line of sight. But that's not, again, very regular. On the other hand, you could have galaxies, two different galaxies coming together and merging, and so then their central black holes will also merge. And before merger, they will be in a spiral, and then they will affect the plane, at the plane that is the inclination of the plane with respect to us. So then we might see periodicities, but it won't be in the form of pulsation. The time scales will be much larger. So, for example, few years. There are a few examples like that, where the interpretation is that there are two black holes and they are spiraling into each other and affecting the plane, the orientation of the plane with respect to us, and therefore the orientation of the jet with respect to us.
Okay. There are a few more questions, and I think those questions were covered during the subsequent explanation. So I would not repeat them. But guys, if you still have those questions and you feel that they were unanswered, please do unmute yourself and go ahead and ask. Otherwise, there are some questions from Sham Sundar Srinivas. So I see that you have put a lot of questions like who would win a fight in a small black hole, an neutron star, or Andre the Giant. So yeah, if you want to just take in, please unmute yourself and go ahead and ask, please.
I think if we ask that question, then Prajval will stop giving presentations to amateur astronomers.
No, but I didn't understand the question. Who would win in a fight? Small black hole, large neutron star, or I don't know who is Andre the Giant. I'm sorry.
He is supposed to be an wrestler or somebody.
Oh my goodness. Okay, that's definitely outside my expertise. And but where is the fight? There is no, so far, no. I mean, I didn't mention any fight between black hole and neutron star. So was that a metaphorical question? Or?
I believe so.
Okay.
Okay, there is one genuine question over there probably. So why black hole images look more like a planet with rings?
Uh, I guess because they're both false color images, and you do have the planets with rings. It's the dust around the planet, and it is driven by the gravity of the planet. Similarly, here it is matter around the black hole, which is driven by the gravity around the black hole. So in both cases, they are sort of, um, you know, driven in these sort of quasi elliptical orbits. So to that extent, it's similar.
I think he's talking about the accretion disk because the ring around Saturn is also kind of a disk, right? So I think that's why even this
Yeah, it is
looks
similar because, if it's a disrupted satellite, for example, uh, then all that stuff would be driven by the gravitational force of Saturn. And here, similarly, the accretion material is driven primarily by the gravitational force due to the black hole. So it's spiraling in. So that way, it's very similar. So the geometry is similar.
Okay. So one more final question. So can an array of telescopes placed in orbit be practical in creating a huge aperture telescope? So you had actually answered this something similar. So if you can elaborate on what kind of similarities that we would require across those orbiting telescopes will be helpful.
Um, Similarity, I mean, it always helps if in an array, if all the telescopes are identical, it helps. With the Event Horizon Telescope, they're not identical. So that adds some amount of complication. On the other hand, the giant meter wave radio telescope in Pune, outside of Pune, or the very large array in New Mexico, of which I showed a picture. There, the elements are all identical, so that does help in the analysis. So, if there were an array built just for the purpose of interferometry, then yeah, I'm assuming that people would build them with similar specs. Um, but there are lots of different factors which go into designing these telescopes. One is the frequencies, because that is hardware. So you have to put in feeds and so on. So that would be one element of the design. The other would be how large will you design each of them, because the larger the each of the elements, the more photons you're collecting, so it adds to your sensitivity. So that is another factor. And then there is the actual structure as to how do you do the placings of these different things, because that results in a certain combinations of pairs projected onto the sky. And then you take into account change with time, so change with the projections as seen by the source you're looking at. And so that would need to be optimized. So that is the other consideration. So there are lots of it's a very complicated process. There are lots of different considerations that go into this.
Uh, Can I ask the next question?
Sure.
Ravindranath here. Hi. It was a nice talk, Prajwal. Learned a lot
Thank
of
you.
new things. What I'm not able to visualize is how do we visualize a stationary black hole as against a rotating black hole? That's something that I learned. Rotating black hole is something that I got to know today. Not heard of.
Um, so you mean stationary versus non-rotating, or you mean
Stationary versus
stationary
rotating, because there was one
rotating?
question I think Aditya asked, is this an image of a rotating black hole, right? So
Yeah. So there have been different ideas on how to measure the spin of the black hole, and the most of these measurements have come out assigning or ascribing some amount of spin to the giant black holes we've seen. There isn't as such an identification that such and such black hole in such and such galaxy is non-rotating. I don't know of that sort of thing. So I don't know if that answered your question, but if you mean how will it actually affect the physics, so there are a couple of different mechanisms to extract energy from a black hole in order to produce, for example, these twin jets. One of the mechanisms proposed does not need the black hole to be spinning. It extracts energy from that stuff that is spiraling into the black hole, from that accretion disk, as it is called. So it is possible to create, collimated outflows or sort of twin exhausts of material without actually having the black hole rotating, as per the theory. But in practice, there isn't a definitive measurement which can say that this black hole is definitely not rotating. And there are many measurements which indicate that those black holes are rotating.
Okay. So it would be fair to say that we don't have evidence as of date that we found a black hole which is not rotating.
I would not make such. I would hesitate to make such a strong statement because it's hard to. It would be, as you can imagine, it would be hard to pin to sort of definitively say that it is the spin is zero.
Okay, got that. Yeah. Yeah. Thanks.
Okay, I see that we are running out of time. So I am still open to one more question. So one more quick question, if anyone has, please go ahead.
Madam, if you have not taken the point of quasars, we would like to get some few details, maybe in 1 or 2 minutes.
Yeah. What do you want to know?
What is quasar and the mechanism behind its high energy?
Okay, so quasar is essentially a historical. It's a historical term, and what all of these things are, they have different names. They're called, some are called Seyfert galaxies, some are called quasars, some are called blazars, BLAC objects. I mean, there are many different names, but all of them, the hallmark of all of them is that they are galaxies with a huge amount of power coming out of their very centers, which cannot be explained by stellar processes. So if you can zero in on how small a volume in the center of the galaxy from which all this power is coming, it will turn out that you cannot explain that by, certainly not by ordinary stars, definitely not even by these very high energy exploding stars. Let's say, you could in principle squeeze a bunch of young stars into a very small volume and have them exploding constantly, so that that whole volume is constantly very shining very powerfully. Even with that kind of phenomenon, you cannot explain the kind of powers that we see. So this is the hallmark. And so for all of these, we talk about accretion around a supermassive black hole. And so quasars also are accreting supermassive black holes, which means that material has reached the close vicinity of the very big black hole that is at the center of that galaxy and is spiraling into it and therefore shining and creating all this power. So in some cases, they create these twin jets are produced, which extend well beyond the galaxy into intergalactic space. That is a small fraction of all the black holes that are accreting, and we don't understand quite why some giant black holes do that and some don't. There are many ideas, but it's not yet it's not yet a certainty.
Yeah, okay. Thank you, ma'am.
Okay.
Hello.
Yeah, go ahead.
Yeah, can I ask you a final question?
Yeah.
Yeah, can you please enlighten me with what is white holes? I've read somewhere in the internet, but was not able to understand it much well.
Actually, I don't know either. Sorry.
Okay.
Okay. Thank you all very much. I want to convey special thanks to Dr. Prajwal on behalf of all members of BAS. That it has been a wonderful session. I personally got to learn so many things that I had only assumed that it might be or may not be. But this session really helped me to understand the intricacies, the some very terms like baseline interferometry and those things. It has been a very knowledgeable session. Thank you very much.
A
Thank you.
lot
Thank
of things
you.
in the black holes are not very intuitive. So just to hear you talk about them and explain this phenomenon, it was really mind blowing. Some of the things like the twin jets. I mean, why can't we see the second jet of M87? So all that explanation just blew my mind. So thanks a lot for that. We had about
You're welcome.
46 people in the chat. So good participation, and you talked for more than 2 hours. I mean, it's very difficult. And thanks a lot for all that.
Oh, you're welcome.
Thank you, ma'am. It was a wonderful experience as a whole.
Thank you. Who is this?
This is Shyam here.
Okay. Thank
Yeah.
you.
Okay, thanks a lot. So, Dr. Prajval Shastri is also on our WhatsApp group. So, if you have any questions, you can probably send some messages on the WhatsApp group. Please keep in touch and see you everyone in the next session.